Alright, we're looking at a brand new Milwaukee 12.0 Forge battery. It's T10 bits, not security for some reason. Right. Have a quick look at the whole thing, but other people have covered this. They've got their blah 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 laser welding and so on, and they've increased the spacing between the cells so that they can have some airflow between them. Not a huge gap between the cells. A mil. This is a brand new battery, never been charged. Oh, let's look at the flash codes. It's on 1 bar. 110011. Day since first charge 0. No, charge cycle 0. Fourth code, factory code is 1, 2, 3, 4. Let's check its cell voltages. 3.5, 3.523, 3.523, 3.523, 523. So all within a millivolt. This circuit board is quite a bit different. This is the last 12.0 circuit board, the previous version on the right. Now under this copper heatsink was 2 large MOSFETs. I never figured out what they actually do. Thrifty Tool Shed has had a look at those. Significantly smaller, as they said. They shrunk the board down so that they could have more airflow getting through the cells. But yeah, so here's the thermistor on the old 12. It's closer to the middle, and this one's right on the end. Not as good a spot for the thermistor, but yeah. Definitely a different look to the metal, not as shiny. It's got more of a matte to it. I'm pretty sure these are the balance resistors here, or the monitoring resistors. Hard to tell what they're actually doing until we test it. So the B plus and B minus are obvious. The center pin is still called charge. So J1 is now called DP/CC, and J2 is now called DC/CP. From the tool to the battery when it's on the tool, and then J2 is the go signal. But then in charging they're kind of reversed. The battery uses J1 to send messages to the charger, and it receives messages on J2. You'd think it'd be like CR for charge receive, and then CT for charge transmit. So D is probably device and C is probably charge. So P is the receiving channel. If the second letter is P, it's the receiving channel. So this is charge P, which means receive, and charge C, which means transmit. This is the charging MOSFET. So charge pin is connected to B plus via this MOSFET. So that MOSFET can control the charge coming in. And that's there to switch it off if, for some reason, the charger stops responding to commands, then the battery can just shut this MOSFET off and prevent charge current from coming in and overcharging. I've got some cool little support brackets here, I guess to give that some rigidity. This thing had a large sort of plastic block built around it, so that's probably a good thermal design. These pins are now more out in the open, they can shed heat a bit better instead of being enclosed in plastic. Definitely the main power pins are a different metal. You can see the colour is quite different, or maybe just a different coating. I'll throw this one in the frame as well. This is the 8 amp hour. So this is what it looked like without the without this sort of copper heatsink with the MOSFETs under it. So this was the old 8 amp hour compared to the new thing, and it looks a bit more similar. The MOSFETs look pretty similar. I'll compare it in a second, but yeah. This fuse is now 15 amp. It was also 15 amp there. Still got this HD1 interface. These pads connect to the microcontroller. Actually, sorry, that's the microcontroller. Big one's the microcontroller. They said they've shrunk the board. Yeah, overall they have. The LEDs are significantly smaller. But I'm pretty sure there's no components on the bottom side of this one. There might be some components here where they've just significantly reduced their number of sort of passives. You can see this one's got a lot more diodes and transistors and resistors and everything compared to this one. They might have shrunk some of them, or they're on the bottom of the board, or their new balancing chip is doesn't need as much. I've looked up all the chips. This first one is a MOSFET, as I said, but it's actually an NMOS. It's a Texas Instruments CSD 18511. Now, it's strange that it's an NMOS because it's connecting charge pin to B+. So that means its gate would need to be driven a good 5 to 10 volts higher than B+, which is very difficult to do. You need a sort of charge pump or something. So I'm not sure how they're actually doing that, or if I just got this thing completely wrong. Okay, main chip, this is the microcontroller, is a Renesas R5F100BEA, and that hasn't really changed from the prior high output batteries. The very first M18 batteries were MSP 430s, but they went to Renesas, I don't know, around about 2019 or something. But the last ones were a BDA, which was a 48 kilobyte bit. This new one is the BEA, which is a 64 kilobyte bit. And I thought maybe they had some sort of program bloat or something, but it turns out that this 48 kilobyte chip is just end of life as of September this year. So the balancing chip, big change. Forever they have been the Texas Instruments BQ76925, and I think every M18 battery has been that up until this one. Potentially the 6 amp Forge was also different. It is a 489250 Renesas. I cannot find any trace of this chip. What I can find is a RAA 489220, which is a 32 pin and about the same size, but that chip does not have any balancing feature. And then they have another chip, which is a 4 to 16 cell chip, that does have balancing, but it's a 64 pin. So I think this 489250 is a new chip that Renesas hasn't put a datasheet out for, or it's a custom chip. So I think what they've done is they've taken this 489206, which has balancing, and it's a 64 pin chip to do up to 16 cells, and they basically shrunk it down to a 32 pin. Anyway, that's going to be fun because not having a datasheet means it's going to be hard to read the I2C comms. Speaking of which, R6 and R8 are still our I2C resistors. The bottom right pin here is clock, and the one just above it is data. And you can see the traces that the clock is going to R8 and data pin is going to R6. Those 3 resistors there, the bottom 2 of them are R6 and then R8 on the bottom. The other thing that's interesting is these ones. These are the monitoring / balancing pins. If there is any balancing, then they will be the balancing resistors. They are 100 ohms. So 12 amp hour Forge, that's your balancing resistors. 8 amp hour, just 8 amp hour high output non-Forge, that's your balancing resistors there, those 5 ones. They don't really look any different in size. 100 ohms is a good sign for the Forge. On the previous ones, the balancing resistors were 1 kilo ohm, which meant a 2 milliamp balancing current. So the change to 100 ohms is a good sign, but that's still not a great balancing current, but that might be what the chip is limited to. The fun part's going to be trying to decode these I2C messages, because we don't have a datasheet for it. We just have to hope that some combination of the other public Renesas datasheets has
a close enough I2C protocol that we can decode it. So yeah, hopefully it's very heavily based on this 489206 and it's got the same registers and everything, and then it'll be easy to see what's going on. Otherwise, I'm going to have to monitor the voltages across these resistors to see if any balancing is happening. Fun times.